So in this video, we're going to look at the second part of the area under the curve exercise 11a, and that's looking at the area under the curve and what we call the definite integral. And so we looked at this website, excuse me, this website in the last video, looking at the Riemann sums. And what we're looking at here is looking at the area under the curve. And so the reason that I want to have a look at this is that I want to explain to you what this means. This is in the textbook. And I want to explain to you what this actually means. So last time we looked at, let me just focus in on this website thing here. Hold on. Here we go. We looked at this particular website here where we looked at the area under the curve. And we saw that if you move the number of rectangles, if you increase the number of rectangles higher and higher and higher, the actual area under this curve is 9 square units. And as the number of rectangles that we use increases, the actual approximate area becomes closer and closer and closer to the actual area. And so what is actually going to happen is we're going to be calculating rectangles of slightly smaller and smaller width. Each time I move this and increase the number of rectangles, the width of the rectangle decreases. And I have to do a height calculation. Okay, so let's explain a little bit about what this whole formula at the bottom actually means, this bit down here. So you'll notice that this says f of x dx. Now dx is going to be defined as our width. So this thing here is our width. And we learned in the last video that if we substitute the x value into the formula, that gives us our height for each rectangle. So f with the x value substituted in tells us what that height there is. And that's what this first bit is. This is the length, if you like, or height. Oops, can't spell length. Okay, so this formula here says length times width. So this is our area formula here. For each individual little x value, that's what that I means, for each individual little x value. And you can see here that we've got a limit as dx, which is the width approaches 0. So what this is saying is as it gets smaller and smaller and smaller, as the width of the rectangles approaches 0, you'll get the actual area under the curve. So this bit here is saying as the width gets narrower and narrower and narrower, and the absolute limit of that width for, now this symbol here, this funny E symbol is the summation symbol, which means you're going to add together all of these particular formulas, which are the areas for the rectangles, for every single x value that you've got from your start x value, so I is your start x value, to your finish x value, so the number of rectangles if you like. So let's just have a look at this again. So as the number of rectangles increases, you can see that the area gets closer and closer and closer. And if I had an almost infinite number of rectangles sitting under there, I would have exactly the correct area. And that's the premise of this whole section about Riemann sums and the definite integral. Sorry, lost my train of thought there for a sec. Okay, so let's have a look at this as a summary. So the actual area is the limit of the sum of the areas of the rectangles as the width approaches 0. Basically it means the narrower the rectangles, the closer the estimate to the actual area. That's what it means. So we also have, so these are the Riemann sums. So we can also use something different, what we call a definite integral, to find the area under the curve. Now later on in the chapter they go through and will join this Riemann sum and this limit formula here with how you actually find an integral, but for the minute that's just what that bit in the book is saying. So let me show you how to do what the definite integral is and how to do it. So the actual area under the curve is given by the definite integral. Okay, so the word integral is what we call this little symbol here. This is an integral symbol, and it's a long skinny S, and you need to make sure it looks like a long skinny S. Sometimes you'll see it quite curved over. You'll see it look like that. As long as it's curvy and S, that's fine. And I kind of think that it can be used to represent, if you like, in theory, the curve. So we're talking about the area from A. So this A is what we call our lower limit or our lower terminal, and this is our smallest x value, okay, the one to the left. That's our A value. We put it down there. So instead of saying the area between x is equal to 2 and x is equal to 5, we put the integral symbol, a 2 at the bottom, and then our 5, which is our upper limit, goes up the top. You can see that that's a much shorter way to write it. So if I wanted to write that, and I'll write this over here, the area under the curve between x is equal to 2 and x is equal to 5 looks like that. That's what that symbol means. And then we have, normally, we don't have f of x, but we'll have the formula for the equation here. And then this very last little bit on the end, the dx, the same as for our differentiation, tells us what the variable is that we are having on our x-axis. What is the variable that we're differentiating, or actually anti-differentiating with respect to? So that's that bit there. Okay. Now this only works, this area under the curve only works obviously if there's curve all the way between A and B. So this is if f of x is continuous for the interval A to B inclusive. Okay, so you need to have a graph across the whole of this integral from this value to this value to be able to find the area. So early on in the chapter, all we need to do is to work out the area using the known shapes that we've got. So this exercise, the questions that they'll get you to do like this, are more about interpreting what this bit at the start actually means, rather than finding a definite integral and understanding how it works. So let's have a go at doing this question. So we're asked to find, now I'll tell you how you say this. This is the integral, whoops, get a pointer, the integral from -2 to 2 of x plus 5 dx. Now you'll notice I've got a little dot here. I like to use a little dot at the end of the expression, just so that you know exactly what the expression is. You don't have to have the dot. Sometimes you'll have brackets. People use brackets to show that that is in fact the formula, but it's up to you. I prefer to have the dot. Okay, so what you'll notice, x plus 5, that's our formula for our function. So our formula for our function or our equation is y equals x plus 5. And we want to find the area from -2, which is our x value, to 2, up here. So this time, what they want you to do in the exercise is to use known shapes. So rectangles, triangles, quadrilateral, different quadrilaterals, you won't get anything other like that. Trapeziums. Sometimes if it's the area under like a sine curve, you could use the area of half a circle. That would make a good approximation. But generally they'll tell you what to do. So we're going to need to find the area under this curve between -2 and 2. So we're going to draw it to see what it looks like. and then we're going to chop it up into shapes that we already know. Now we can use a trapezium to do this, or we could split it at this level here and find the area of the rectangle below and the area of the triangle above. But to do that, we need to know the y value at our end points for each of those points to be able to find those areas. So the y value at -2, when you substitute -2 into our formula x plus 5, you get -2 plus 5 is 3. So this is the point -2, 3. And for our x is equal to 2, we substitute it in and we get 7. So this is the point 2, 7. And so our area under the curve is equal to the area of the rectangle at the bottom. So the rectangle at the bottom is, there's a width of 2 here and 2 here. So that's a total distance of 4. So our area is 4 times the height of our rectangle, which we just worked out to be 3, because that's a 3. So 4 times 3 plus the area of the triangle that sits above that. So the formula for our triangle is half times our base, which will be the same distance there as it is here. So that's a 4, times by the height of that triangle, which will be the difference between 3 and 5. So that distance here is in fact 5 minus 3, which is equal to 2. And then we simply work out our area. So that's 2 times 2 is 4, so our area is 16. And that's how they would like you to do those particular questions. So what you need to do until you learn how to do differently is, number 1, do a sketch. Number 2 is divide it into shapes. Number 3 is to find the area of the shapes. And finally, number 4 is to add the areas together. Now, normally if we're finding the areas of something under the curve, and even in our last lot of questions, we were using square units to make sure that everybody knew what we were doing. And so what we've got here though, our definite integral, we can work out using area, but the integral itself is actually only a number. So our area will be units squared, make the pen work, units squared, but our actual integral is actually only equal to the numerical value, because our integral doesn't necessarily have to be an area under the curve. We can use the area under a curve to represent the integral. So if you're doing a definite integral, you don't need to use any units.